All right. So we hopefully know what the semantics, or vaguely know what the semantics of the, or syntax, of the RDF is. Well, how does that syntax, what's the architecture, what kind of architectures do we use, IT architectures, to implement RDF-based systems, so a semantic web architecture? It's not much different from a web architecture, to be honest. It's got the same kinds of components. First of all, there's a database, and there are databases that are specifically designed to call triples, and they tend to be called triple stores or RDF stores or things like that. So there are databases specifically for RDF storage. You can also, there are extensions, for example, to Postgres that allows you to store RDF in Postgres. So it's also, that may be a relational model in which you're storing this graph-based data, or it may be a dedicated triple store database. So we've got a database that does the storage. Then we need to get data in and out of the database, just like we do into a relational database. So there are various parsers and serializers for loading text tables, text-based data into your RDF database. There are also, well, as we can see, other ways to get data in. There are converters and scrapers designed to extract triples out of semi-structured and unstructured text on web pages or other documents or things like that. If you think about it, this is probably more practical for RDF than it is for many other sort of database models, the relational database model, because the data that you get out is often very sparse. You might have just a few items of data, and you can see that an RDF triple is storing a very small amount of information. Okay, it's not a table. You don't need to fill a whole table up and have lots of blank spaces. All you need is a few arguments, a few statements to extract from a text document, then you've got information out of that document. You need, when you do a query, the parts of the various graphs or the triples are extracted out of your triple store. Needs to be able to merge the graph to create your graph model from your triples that you've extracted out on the basis of your query. So you have a query that extracts triples out. Those triples are then, doing this the wrong way around. You have all these triples in your RDF store. The database itself, I think, merges the triples into a graph. Now, whether it stores the individual triples separately and then dynamically creates a graph, or whether it creates, every time you add a triple, the graph, it stores a graph model that's then expanded on the basis of the triples that you add, I honestly don't know. It wouldn't surprise me if their different database approaches took different models on that, depending on how many triples you had. If you had millions and billions of triples, I could see that basically building the graph and then just changing the graph when you've got new data might well be a good solution rather than building the graph every time you need to do a query. So it wouldn't surprise me if you can do both ways. Either the graph merging is part of the query or the graph merging is a pre-step before any querying. I can imagine both situations. You need to query the graph. How do you query the graph? Well, there's a language called Sparkle. And Sparkle is the query language of the semantic web. And Sparkle is what's an example of a recursive acronym, because it stands for Sparkle Protocol and RDF Query Language. So Sparkle is part. That's what we mean by a recursive algorithm, where part of the abbreviation or the acronym is embedded within the acronym itself. So PHP is I think of it as personal hypertext processing, but other things think it's called PHP in hypertext programming or something. So it's just an aside to that. And then you need some kind of application that sits on top of the database engine and provides the user interface, or the friendly user interface. So it's very much similar to a relational architecture. You're just replacing your database, your relational database, with an RDF triple sort. Oops. Sparkle. Such a nice name. Right. We have a graph. We want to make a query. How do we query across the graph? So, who directed the films James Dean starred in? We've got our graph. We've got James Dean played in the 3 films that he was in: Rebel Without a Cause, Giants, East of Eden, and then the directors by the people who directed those films. 2 directors here because I believe George Stevens started directing Giant, then couldn't complete the job for some reason and got replaced by Fred Wheel. Hence you have 2 directors for film Giant. I'm not going to go into how Sparkle works because I have no idea, basically, the underlying operations. But the syntax we can look at here. Basically, what happens is you write a query string in which the parts that you're trying to identify are identified by these question marks. So we write a statement like James Dean, colon, played in. So there's our object. There's our predicate. Then this is what we want to know. This is a question. We want to know the answer to this. We want to know which films he played in and what appears twice, because these are 2 sets of predicates. Yep. So the first one tells us James Dean played in what films. That's the first thing we need to know. We then need to know what, being this value, the value of the films that he was in, directed by whom. And that's the general sort of syntax of Sparkle queries. And the answer that you get down the bottom, if I can make that out of the way so it's, don't know how you make this vanish. We look down the bottom, we've got 3 watts. Oh, 4 watts here. 4 watts, because we get 2 watts for this one. Giant, or we get 4 responses. We get what, Giant, who, George Stevens, what, Giant, who, Fred Greenhill. Those are the 4 returns that we get from our query. Where is, what RDF? Why do we care? Does it exist in the real world, or is this just a fantasy of some information technology programmer? It's out there and it's growing. It's been a slow start, but it is now starting to become a player on the sort of data landscape. So the land registry, which is the registry of who owns what land in the UK, as far as I understand, it's not like anything I'm an expert in, provides a Sparkle query interface to its data. Not only does it provide it, this is the only way to query the land registry database offline. There is no API defined. You can't download a dump of the database. There's no online friendly query form. You have to use Sparkle, from what I understand. And when you go to the land registry, yeah, I'm not sure what the rationale behind that is. They're going to be a leader. They've got complex data. I think that's one of the things that they... Can you? Right, okay. Well, I was very surprised, I think, when I looked at this, and I couldn't find another place to get the data. So that may be simply an example of my ignorance, but they certainly do have now this Sparkle query as well. I couldn't find an API, certainly. When I looked for an API, I couldn't find one. There may well be a single location search web thing. That wouldn't surprise me at all, but not a general search engine, I think. But it'd be interesting to know what other, because that's a very interesting sort of implementational question. Why have they implemented a Sparkle query engine rather than any other, say, an API, put the resources into developing a more standard API? Anyway, so you go to the land registry linked data page. Basically, it provides you with a text block within which you can write your RDF query. This is the default that they say that it opens up with. Here's the links, the pointers to the various namespaces involved. This is the actual query structure here. And you can see it's got some elements, Sparkle's got some elements of things, syntax that you would recognize from SQL. So we can read this relatively straightforwardly, he says, optimistically. Select distinct, well, we know what that means. Region name, year, month, index, or a list of attributes to return. Where, having a conditional where clause. The values, question mark Plymouth, so the value is Plymouth, is within the definition of the city of Plymouth. Within that is part of, where the value, the place, is within Plymouth, where Plymouth is defined by this URL. Then, not quite sure what happens under there. Okay, Sparkle query language. Clearly, I am a very beginner when it comes to Sparkle query. I've only ever played around with it a couple of times, but that's what we're looking at. So far, we've looked at RDF. And to a certain extent, RDF supplies a very basic list of concepts for predicates. So what's happened, to get more semantics into our models, they started off with RDF, which basically defines triples and things like that, and allows a few basic concepts. But we need more advanced concepts as well, and those concepts are added in through the namespaces RDFS and OWL for Web Ontology Language, although obviously they can't get their letters in the right order. So RDF itself has very limited semantics, as you said there earlier. It was a directed graph. Anne Hathaway was married to Shakespeare, but we couldn't argue back the other way that Shakespeare was married to Anne Hathaway because it's not we don't have it as a symmetric. We know it's a symmetrical relationship, but the computer doesn't, and the way the model is defined means it doesn't know. So RDFS adds some additional semantics, full class structures, and also restriction domains for values, just like you have in a relational model. Your values can only be between, say, 0 and 100 for a percent. So RDF and the extension RDFS define a limited set of these relationships, predefined relationships. If you want a much more richer semantic description language, you need to use OWL. An OWL namespace includes definitions like inverse of. So for example, Ben is my son. If I know the inverse of father and son, then we can define back the way that I am Ben's father, and vice versa. We can define, also allows superclasses to be defined. It allows us to define that two concepts, two ideas are equivalent. So in one set of RDF, we may have the concept of taxi or something, and in the other one of hired car, or hired driver car, where you hire a car with a driver. Those are effectively similar things. They're not quite the same, perhaps, one could argue. But imagine a situation where you've got the same thing in two lots of RDF, but you're using different definitions. We can define a triple with the equivalent class as a predicate to say that, in fact, these two different sets of words in these different ontologies are, in fact, mapping onto the same thing without needing to point to the same URL. because they're differently defined in different namespaces, they will have different URLs that they point to. So basically, OWL allows you to add on extra types of semantic relationships, which improves and means we can do more complex reasoning across our graphs. So it allows us to create graphs that are like this, which is all to do with vessels, deployed vessels, whether in service, whether they're out of service. We can use RDFS domains to define valid values onto particular objects. We can define these subclass relationships with RDFS. So these are all three subclasses of vessels. They're all vessels. That's one that's deployed. That's one in service, whatever that means. That one's one that's out service. And they are all subclasses of vessel. And as we know from our understanding of object models, that means that all the attributes associated with vessel are going to be applicable to these subclasses as well. Same with all the methods. So we can create these more complex graphs. And really, I'm only going to leave you with that knowledge that this is how you build up more and more of these complex ontological relationships, which allows more and more complex reasoning. I think we're going to leave it at that level rather than going into the details of how those reasonings operate. So where's geography in all this? We've learned a bit about Shakespeare, maybe we have, but we're geographers. Where does geography come on? Well, the geosemantic web is simply where we try and implement geographic information in a semantic web model. It's presently, I understand, a work in progress, but I may be out of date. This moves very quickly. I try and update these things most years to check whether anything progress has been made, but I didn't have time this year. So basically, in 2003, the W3C started an interest group deciding how do we implement geographical concepts, coordinate systems, etc., in the semantic web, and they came up with a basic RDF model for storing WGS84 points. Probably going to be 2003 to 2005, they started working on GeoOwl for representing geospatial concepts. So GeoOwl would include concepts like within, topology, topology constraints and things like that, connected to, must be adjacent to that, all those kinds of relationships that we're used to. But neither became W3C standards. And then in 2015, there was a sort of reboot between W3C and OGC to further agree standards. So what this basically means is that there is no agreed standard for spatial data in RDF, and that triple stores vary in how they support spatial data. It's usually pretty minimal. There is an OGC specification, basic specification for GeoSparkle, which is the geographical equivalent of Sparkle, but for geodata, so a geographically enabled Sparkle query language. I really need to know some more about that. So GeoSparkle. So here's an example of GeoSparkle query. What are all the geometries within 10 kilometer of the feature described by that URL? And the query select what, where, etc., etc. There's no point in me reading out that text to you, but you can get an impression that you can write geospatial queries just like equivalent way to how you would write them in SQL, but in Sparkle. And that returns a set of these geonames. If you want to try out some GeoSparkle, go to geosparkle.org, and you can get some examples you can have a fiddle about with some Sparkle queries, see if you can get them to work. There's some good examples here, and like most things, if you can take one of those examples, then you can adjust it and play around with it and learn a bit about it. So I'd advise you to have a little look at that. And the query there, we run it. What do we get back? We actually get just a table of data like this. After all, there's no reason we're not necessarily kicking out triples. Unlike in a relational model where your input is always tables and your output is always tables. In the relational model, your input or your data structure is triples and the graph, which you build into a graph, but your output can be any format you like. So in this case, it's in a tabular format. There is an effort to create linked geodata. So this is taking the linked data guidelines of the linked data guidelines and applying them to geodata. This is the group, the website of the group that's attempting to do this. I know very little about how much progress they've made on this. Another example of where linked data is being used, there is an OSM, OpenStreetMap, linked data effort or whatever version. So you can, there's this linked data, geodata.org provides a linked data-based browser for updating, viewing and updating OSM data. So you can access it through there. It's another example of where it's being used. Okay, rather sketchy overview of the semantic web. As I say, web of data rather than documents. It's an emerging technology, but it's been slowly emerging for 15 plus years now. And that is not unusual, to be honest. It takes usually a decade to 2 decades for stuff to come out of the laboratory, out of the test environments, to being generally used across business environments and generally used across many different environments. So while I think the jury is still out on how big the semantic web is going to be, I think it will be a component of the World Wide Web and data on the internet for the conceivable future. And it does provide an alternative model to data, access to data, and one that has distinct advantages over other approaches, specifically for things like being sure that you're actually talking about the same things and the data that you're collecting and joining together is actually about the same concept or the same type, the same object. Having said that, my personal view is it's probably way too complex for many needs. You know, this is overkill. And where it really stands out and its usage is, its greatest potential is where you've got these disparate data sets that are in different silos and you're trying to extract and bring those data sets together to create a new data product from those previous separate information sources. Because one of the great problems when you bring data together that's been collected by the different organizations in different ways is this connecting things. When they talk about London, are they, in this data set, is in fact the same definition of London that we're using in this other data set. And there are many different definitions of the extent of London. All right, I've forgotten we had that one. Just a little table there, let's have a look. I've forgotten about that. So that's the 3 data models that we've met in this module. We've met the relational model, we've met the object model, and we've met the semantic model. So 3 different models. So clearly a semantic model only in a very small way. So I knocked up this table which just tried to contrast these data models. So The relation model is based on tables, columns and rows, the object model on attributes and methods. The semantic model, the base item is the triples. The function of the relational model is basically to manage and control data. It's about maintaining consistency. It's about preventing your data getting inconsistent. That's what its one of the major functions of the relational model is. Hence all the constraints, the domains, and everything else. Same with the object model. The semantic model, I would say its main function is the integration of data from different sources, rather than using data and building one integrated data source up from the beginning. It's more about bringing data together from different locations and merging them together. Integrity in your relational database is defined by your DB schema with all the constraints that you impose upon your DB schema, your foreign keys, your primary keys, your domains, all that kind of stuff. Integrity in the object databases or the object model is maintained in theory by the concept of encapsulation, if you remember encapsulation, the idea that you can only interact with an object through its methods. And therefore, if the methods are well defined, you can only interact with the object in a sensible way. In the semantic model, that integrity is enforced by the ontology that's built to describe the semantic relationships between the objects in the data objects. Redundancy in the relational model, well, your normalized database schema, the whole aim of it is to remove the redundancy. In the object model, redundancy is maintained by, I've got object classes and component relationships. So how you define the object is, if you define it well, there shouldn't be any duplicate information in the object. If your object classes are correctly defined, your attributes should be defined at the correct level in your hierarchy, also preventing duplications. In the semantic web, redundancy is inherent in the triples. If there was no redundancy or between the objects, then you wouldn't be able to collapse your graphs. And it's the collapsing of the graphs which removes the redundancy from the